fixed it.
Oh, good.
Yeah, they forgot to give me access. Cause I'm just this humble little
What do you?
hermit that lives in a cave and no one thinks about it.
On the left. Now you got all the tablet tickets, right?
Yeah.
Hey, guys and girls. Like to see everybody's face, please. All right, before we get started, I just want to remind a few people that I want you to stay after class because we need to set up some Zoom meetings. That would be Matt, Leonard, Dylan, C, and James Kelly. All three of you need to stay after so that we can set up a time to meet tomorrow. Let's see. How was your spring break? Did y'all go somewhere? No? Or did you stay on campus or did they make you leave? I'm just curious.
They didn't make us leave, but a lot of people left.
Yeah, I imagine a lot of people just went home, right, to be with family. I went to Park City. I skied. It was awesome. Anybody do anything else? Anybody go anywhere? Anybody go skiing? No? How are you guys doing? Are you okay about being back? Everybody okay? You guys don't look very happy. Have you had other classes today? Yeah, so you're kind of in the groove. Which day? Is today the first day back or was yesterday? No, yesterday was, I guess, right? For you guys? Yeah. Okay. So I graded all of the chapter 2 and 3, and I've been in touch with some of you, those of you about your grades. You guys know that I really want you to succeed. I hope you know that. And those of you that have asked for help, I've helped you, I've given you extensions, whatever. I'm reasonable. So don't just shut down, okay? I'm here for you and I want you to do well and I will help you to do well. And everybody I think that I've worked with has benefited from asking for help. So please, I know sometimes, you know, what you're doing is tough. I know some of it's online, some of it's face to face, and then they, you know, take you out of quarantine and all of that. But just know that you guys can ask for help. I just, please don't shut down if you start to lose it. And it's, you know, reasonable that you would, because this is tough what you guys are trying to do. Drew, you have a question, honey?
Yeah, when will we be able to see the test on Wiley?
You won't. You will see your grade on the grade book in Moodle.
Okay, so we'll never like see what we got wrong.
No, because it
Oh,
was digital, which is
okay.
kind of a bummer. But you know what? Let me make a note of that and let me see what I can do about letting you see it. Well, one thing I will tell you that there's a few people that really had extenuating circumstances and haven't had a chance to take it yet. I have somebody taking it tonight at 9:30. So I definitely can't share anything with you until after everybody's taken it. The other thing is that because you took it on Wiley, everybody got a different question unless you took it in class that day. So I guess what I could do is publish the key. How could I do that? I don't know. I'm going to need to give that some thought, guys. Okay. But you could always set up an appointment with me directly and we could go through every question that was on the test. So that's another option for you too. Okay. And please know that I'm willing to do whatever you want in order to be comfortable about the material. Okay. Also, you should know that the final exam review will be very, very comprehensive. So I know a lot of times you want to go back through other tests to see like these are the things that I missed, but the actual review for the final exam is almost exactly like what you're going to expect. The numbers are just different. So this is an applied calculus course. This isn't meant to torture you. It's meant to have you relate basically your algebra skills that you learned in high school to calculus. Anyway, so don't anybody freak out. Also, I had a couple of people say, gosh, I didn't do very well in the 2 and 3 tests, but it's just one test, right? And you have many tests, you have many homework assignments, and you have the final exam. So if you screwed up on one test, it doesn't mean you're going to fail the class, okay? Anybody have any other questions regarding that? You guys all feel good and you know that I'm behind you and I'm here to help you?
If we took it on paper, are we going to get that one back?
Probably not, because I think we are going to be, at least I am going to be, I guess I could take a picture of it and give it back to you. I could do that. Paper test. Okay, and Will, I appreciate the question. Again, I need to think about it because the nature of this course. I am back in Florida with my dad, who's not doing great. So we are not going to meet face to face at all anymore. So we're going to be online for every class, which means that all your tests will be online and they'll be on Wiley. And your final exam is also, I'm sure you guys have heard that all final exams are going to be online as well, just because they don't have enough room to house all of you guys and keep you safe, keep you 6 feet apart. Okay, so what we're going to do today is we're going to go into a new chapter 4, which is taking basically everything that we've done and kind of putting it together. So we're going to, all of chapter 4 is about using derivatives, and today's lesson is going to be about using the derivatives and kind of relating it to the graph of the original function. Like, what do certain derivatives, first derivatives, tell you? Where could you find those things on the graph? And then we'll go into second derivatives too. And what does that tell you? And how does that relate to the graph? And some of this stuff is interesting because you guys will recognize, okay, I remember a parabola, right, in Algebra 2, and they gave us this formula for the vertex, but I'm not sure where it comes from. So we'll do some interesting stuff today. All right, let me share my screen. All right, can you guys see my notes? Wait, I got it. I can't see you guys right now. I need to put that on my other screen. Here we go. All right, cool. So you can see my notes? All right, cool. It's been a while, right, since we've all gotten together. So I've had to remind myself, like, how do I get to my Zoom again? All of that. So. Okay, so chapter 2, as we saw in chapter 2, values of a function and its derivatives are related as those rules say. I'm going to come back to those rules in a minute. But let's say here it says sketch a useful graph of this function. Now, there's some stuff that we already know about a cubic function, and that is, I'll write this down. That is that a cubic function is S-shaped, right? You know, like we know it looks something like this, right? Cubic. So we don't want to forget what we already know. We know that it's S-shaped. If you were to graph this function here, if you were to graph this function on a 10 by 10 window, or negative 10, right? By 10 window, you'd get what we would call a pretty useless graph. Which would look something like that. Today, when I was going over these notes, a lot of the pictures were corrupted. So if you printed this out yesterday, it's going to look a little different. Mainly the pictures will be different, but it's basically the same. If you printed it out within the last half hour, you have what I have. All right, so, okay, so what we could probably say is that this graph might look something, like this, right? That looks kind of S-shaped. It might look something like that. But in calculus, we're going to be interested in the local maximums, the local minimums, and then later something called an inflection point where the graph will change from convex down to convex up. So my point here is that this graph is pretty useless. So in Algebra 2, you guys learned how to use your windows, right? And you know, make the graph more usable so that you can see the highs and the lows and where it crosses the x-axis and all of those useful things. So we're going to take this idea and pretend like we can't control the window. We need to figure out where these things are using calculus and derivatives. So the first thing we're going to look for is we're going to find out where the first derivative is equal to 0. So you're going to calculate the first derivative here of this function, this cubic function. So we'll say that, let me go back to black. So we can say that the derivative of this function, this x cubed function, is going to be 3x squared, right? We're just using the power rule, minus 18x minus 48. And of course, the derivative of constant 5 is just 0, so it goes away. All right, so once we figured out what the derivative is, we're going to set it equal to 0. And then once we set it equal to 0, we're going to solve for x, because this is going to give us what we call one of our critical points. So if you solve this, you're going to factor it. And of course, you'll factor out the GCF and then factor the resulting trinomial to get x minus 8 and x plus 2. And then, of course, from there, you're just going to set each factor equal to 0 and find the solution. So you would get x minus 8 equals 0 and x plus 2 equals 0. Of course, you don't have to set the 3 equal to 0, right? Because you could divide the 3 out on both sides. So you would get these important points, x is equal to 8 and x is equal to negative 2. All right, so far we're going to start getting kind of a useful graph, and I'm just going to sketch a graph here. Let's see. Let's say this is like negative 10 and this is positive 10. And this is not to scale. Oops. Okay, so what we have here is we've got this point at negative 2. So let's say this is negative 2. And then we have another point that's at positive 8. So let's say it's here. Okay, so now what we're going to do is we're going to use the zeros of the derivative to find critical points. And what we have so far are critical x's, but we need the y's that goes with those x's. So to use those zeros, all we're going to do is find out what the derivative at negative 2, sorry, not 2, at negative 2 is equal to, and the derivative at positive 8. So if you put negative 2 into the derivative, which we got was 3x squared minus 18x minus 48, then you would get 104. And if you put 8 into the derivative, you'd get negative 396. So what we find here is we've got this point now that is, use this real quick here. We've got this point that is negative 2, 104, and 8, negative 396. And now you can kind of see why I put the points above the axis and below the axis, because I knew that it was going to be above because it's the y value of 104. Okay, now what does this mean? The derivative, when the derivative is 0, that means that the slope at that instant point is flat, right? So if we're using the derivatives, what we know is that this is going to be the top of the graph and this is going to be the bottom because the slope is 0, right? Okay, let's see what else we can find out. Now we're going to use the derivative on certain intervals to figure out if the graph is increasing or decreasing, right? So we've got this area that's less than negative 2. We've got this interval that goes from negative 2 to 8. And we've got another interval that goes from 8 to infinity, right? So there's 3 different parts of this graph. So we want to know, well, is the graph going up here and then maybe coming down and going up again? Or is it going down here and then coming up and making the S that way, right? So this is how we're going to figure it out. Okay, so here we're going to use the derivative on intervals, and those are the intervals that I just discussed with you. So let's see, we've got negative 2, and then it goes to positive 8. So these values over here are x's that are less than negative 2. These values in between are when x is in between negative 2 and 8. And the values over here are when x is greater than 8. So what we're going to do here is we're going to use test values to figure out if it's increasing or decreasing. And we're going to use the derivative to do that. So let's pick a test value and find out if it's positive or negative. This is called the first derivative test. It can tell us whether the graph is increasing or decreasing during that interval. So let's see, a test value that's less than negative 2, we'll just go negative 3. You could go -5, it doesn't matter, but I try and stay fairly close to that number. If you put a -3 into the derivative function that we got above here, this 3x squared minus 18x minus 14, then your result is going to be a positive 33, which means that the derivative or slope at that point is greater than 0. Right? So that will tell us that the original function f is going to be increasing. In that interval. And then if we do the same thing for the interval between -2 and 8, let's pick a number. I picked 0. And that will give you -48. So that means that the derivative or the slope at that point is going to be less than 0, and also tell you that f will be decreasing in that interval. And then do the same thing here. Let's pick 10. That's a number greater than 8. If you put 10 in the derivative, you're going to get a positive 72. So that means the derivative or slope at that point is positive, right? So that'll tell you that the original function f must be increasing. Okay, so if we go back, we know that in this interval it was increasing, in this interval it was decreasing, and in this interval greater than 8 it was increasing. So now we can draw a pretty decent graph, right? Much more useful, right? We know that that's going to be the maximum, local maximum, and then this is going to be your local minimum, and then we know that it's increasing that way as well. And remember, the derivative is the slope at a particular point. So notice that the derivative at this point right here is 0, right? It's why we set the derivative equal to 0. We wanted to know what that resulted in the original function. So that's called the first derivative test. There's something called the second derivative test, which uses concavity. So, and remember from prior lessons, the second derivative will tell you if something is concave up or concave down, depending on if it's positive or negative, right? So we're going to do the same thing here, but this time we're going to take the second derivative. Notice these are two derivative marks too. Sometimes it's hard to miss those. This is the second derivative. Okay, so now we're going to first find the second derivative. So we know that the first derivative was equal to 3x squared minus 18x minus 48. So if we find the second derivative, we'll just do the power rule again here. So you'll get 6x minus 18. Now this is where we're going to get our intervals for concavity. So we're going to set 6x minus 18 equal to 0 again and solve for x. You'll get x is equal to 3. And then let's set up our intervals. And notice here we got 2 zeros, right? So that's why we have more than 2 intervals, right? We're here, we're only getting 1 0. So we only have to set up intervals, only 2 intervals. Now, if it's not 3, then it's going to be, all of these values will be x is less than 3. And if it's in the other interval, it would be all the x's that are greater than 3. So we're going to find the second derivative of a number less than 3 and the second derivative of a number greater than 3 and see if you get a positive or negative number. Let's see. Okay, so what did I choose? I chose a number less than 3 is 0, and a number greater than 3 is 5. You can pick different numbers, it doesn't matter. Well, if you put 0 into the second derivative, 6x minus 18, you're going to get negative 18. And if you put 5 into the second derivative, 6x minus 18, you're going to get 12. So negative 18 is, so you can say f prime, oops, let me switch back to black. So you can say the second derivative is less than 0 here, and the second derivative is greater than 0 here. So if it's less than 0, you know from a prior lesson, and also above here, these rules here. We already used these rules earlier. So you know that if f is increasing, then we have, sorry, if f is, so I'm on the wrong section, here we go. If the second derivative is less than 0, that means that it's decreasing or concave down. And if it's increasing, it's going to be concave up. And let's just double check that on our graph. So we're talking about where 3 is, right? Let me give you a minute. It looks like you guys are writing. Okay. So let's look at where 3 is on our graph. That was just a sketch graph that we did. Let's see, 3 would probably be somewhere around there, right? And notice what happens in the interval of x is less than 3, we have concave down. And in the interval here, where x is greater than 3, we have concave up. So it all checks out. And that's kind of like an overview, right, of how everything is sort of related and how you can find highs and lows. Any questions so far? Let me move this back down here. Matt, Dylan, Will, Thomas, Connor, come on, guys, I want to see your faces. Thank you. All right, everybody ready to go? Okay. All right, now here, there's what I just showed you was kind of the gist for this section, 4.1. I'm just going to show you all the different ways they can ask to see if you understand the theory behind what I just did. Okay, so to review, the first derivative test says that if the first derivative changes from negative to positive, it's called a local min. If the derivative changes from positive to negative, then it's a local max. All right, also this critical points, we'll look at that in a second. Okay, so it says use the derivative to find all critical points and classify each critical point as a local min or a local max using this rule up here. So first, let's find the derivative. We're using the power rule, right? So you have 3x squared minus 75. Then we're going to find the critical point by setting that derivative equal to 0 and solving for x. And then, of course, you would factor the GCF out and then factor the remaining. I'll do this for you just in case you get lost. Then this is just the difference of squares pattern, right? So we just have x plus 5 and x minus 5. So that's completely factored. Then we take all the factors and set them equal to 0. So we get x is equal to negative 5 and x is equal to positive 5. Now, in order to figure out if it's a local min or local max, we're going to set up an interval table, right? So we know that one critical x value is negative 5 and another critical x value is positive 5. Better than that. Okay, so these are the numbers less than -5. These are the numbers between -5 and +5. And these are numbers greater than 5. So I'm just going to use test values again. So let's see, number less than -5, I used -6. So if you put -6 into that derivative, 3x squared minus 75, you would get -33. That purple color in case somebody's not here today. So here we're going to use -6. Here, what else did I use? I used 0, number between -5 and 5, and then a number greater than 5 is 6. Again, you can use different values, right? So f prime of -6 will give you -33. So uh-oh. So that means that oops. Well, let's just fill out the values here. This is f of 0. Is that -33? Maybe I'm not doing that right. -6. That would be 36 times 3. No, that would be a +33. So what this means is that f prime, I forgot that put it as a negative. All right, so what we have is f prime is positive, right? So we know that the original function f is increasing. And all right, and then if we did f of 0, we're going to get a negative number. And that would be -75. And if we did f of 6, you would get +33. So here we know that the derivative is less than 0, so we know that f is decreasing. The original function f. And here we know that the derivative at 6 in that interval x is greater than or equal to 5 is greater than 0. So we know that f, the original function, must be increasing. Okay, so we're going increasing, decreasing, increasing in these intervals, right? Now this is where we're going to use the rule here. If the derivative changes from negative to positive, you have a local min. If it changes from positive to negative, you have a local max. So here, I want you to be able to see this. Negative to positive, that would be here, right, at 5. So if it goes from negative to positive, you have a local min. And if it changes from I wish you could see this thing, changes from positive to negative, like it did here, right? Positive to negative, then that's how we know that at -5, we have a local max. So the overview that I gave you in the last page, that's kind of like the whole shebang, right? But they're not going to ask you the whole shebang for every single question, right? Here, notice they just want you to find the critical points. To find critical points, you're going to set the derivative equal to 0. And then to answer the question whether they're local min or max, that's when you set up the interval table and do your test values. Any questions? You guys need a minute? No, everybody ready? Okay. Connor, looks like you're sitting outside. Is it nice in Baltimore? Oh, no, sorry, that's a Daphne. Daphne, you're outside. Is it nice?
Yeah, it's really nice out right now.
Wow. It's like in Florida, I'm here. It's 80 degrees today. It's really nice. Okay, I'm happy to hear you guys are having good weather. That's good. Then I don't feel as guilty for being here. Okay, example 2, graph the function and describe the location of the critical points and where the function is monotonic. That means where it's increasing or decreasing. Then use the derivative in algebra to explain the shape of the graph. Okay, so I graphed it for you just using Desmos, and you guys are perfectly welcome when it says to graph something to use your calculators. Don't feel like you have to graph it from hand like I did on the first page. You do not have to do that. I just want you to be able to understand how the derivatives relate to the different parts of the graph. Okay, but you're welcome to use a graph just like I did here. So we're just going to verify what shows up on this graph, right? I would say that just looking at the graph itself, right? Like if you guys graphed it on your TI-84, this is pretty clearly a local min, right? We can also say that on this side of the graph, this is decreasing. And on the right side of the graph, it's increasing. So let's see, how does that relate to the derivative, right? And then the 0 of the derivative as well. Okay, so we're going to take the derivative of this function. So we'll get, the derivative of e to the x is just e to the x. And the derivative of 10x is just 10. Now we're going to set that equal to 0 and solve the equation. So the first thing I would do is bring the 10 to the other side. So I have e to the x equals positive 10. And now to solve this problem, when you're solving for the exponent here, you can just use natural log, right? So we can say natural log. I remember that's a little, the index there is a e, right? It's just implied, right? So if we take the natural log of both sides, then because we've got this, we can just dump the ln base e of e, and you just get x by itself. So x is equal to the natural log of 10. And remember, natural logs are just numbers, right? So the natural log of 10 is just, if you put this in your calculator, it's about equal to 2.3. So look what we just found. We just found the x value, 2.3, of the local min. And then there's some y value there, right? Now let's take that 2.3 x value and make an interval table. So we want x's that are less than 2.3 and x's that are greater than 2.3. And this will just validate our graph where it's decreasing and increasing, right? So we're going to use test values. So a value less than 2.3, we'll just use 0. That's easy. If you put that in, you would get -9. And if we do a value greater than 2.3, let's just say I used 5. Then you would get this number, 138.4. Well, it kind of, it does validate what we got on our graph, right? Because the derivative here is less than 0. So that means that f must be decreasing on the interval between negative infinity and 2.3. And then here we have a positive number, so the derivative is positive for the values that are greater than 2.3. So that means that on that interval, f is increasing. So it just sort of validates what's happening in the graph, right? With the derivatives. Any questions so far? Everybody okay? All right. Now, again, the first page was really the whole shebang. This is just a different way that they can ask you. Okay. So it says, let f equal a continuous function with a critical point that satisfies f of -2 equals 104. Now, notice that that's saying f, not f prime. So they're saying that in the original function, if you put a -2 in, you're going to get 104 out. And then it also tells you that f prime of -2 is equal to 0. Right? And remember on the first page, if f prime is equal to 0, that would be here, right? On the graph. So what are the coordinates of the critical point? Well, we can say that since f prime of -2 is equal to 0, that means that the x value on the original graph, the critical point must be a -2, right? Because they're telling you that the derivative at that x value is equal to 0. So since that's true, then you can say, and this is where this other rule comes in up here. Where is it? Oh, don't want to use that color. Let me use something else. Here. Then we can say that whatever that p value is, in this case, since we know that the p value that makes the derivative 0 is -2, then we can also say that p f of p, right, or x and y, right, must be a critical point. So let's calculate this. Well, we know that p is -2 because we know that the derivative -2 is equal to 0 at that point. And then they give us that f of -2 is 104, right? So f of -2 is just 104. So the critical point that we just found is -2, 104. And then to figure out if it's a local max or a local min, we're going to use this other bit of information they gave us, right? And we'll say that since the second derivative at -2 is equal to a negative number, then it must be concave up or concave down. That's a question for you guys. What do you think?
Concave down.
Yeah, thank you. And that's just the second derivative test from the other page, right? So if it's concave down, then if you think about it, it's got to be like this, right? And the -2 is here with some y value. If it's concave down, and the point at which the derivative is 0 is up there, does that make it a local max or a local min?
Max.
Yeah, definitely a max, right? A min would look more like this. and therefore a local max. Let's just say second derivative test. Okay, let's see if your graphs, no, they didn't show. Okay, so I'm going to just kind of sketch a couple of graphs here. So we want to see how many critical points on the graph, and if the points are local min, local max, or neither one. Now remember, critical points happen when you change from concave up to concave down, or when you have a local min or a local max. So let's see. Here, you had something that looks like this. Oh, that's not a very good drawing there. Let me try that again. There. How many critical points do you think are on that? Remember, it's where they change concavity, or it's a max or a min. Well, it definitely has a local minimum, right? But it also changes from concave up to concave down, right? So this is change concave up to down. And the name for that is what we're going to do when we get to 4.2. We might as well put it up here. This is called the inflection point. So in this case, it's got 2 critical points. So this would be when concavity changes or highs and lows. All right, so we know that one of these is a local min, right? And the reason why it's a local min is because it is decreasing and then it's increasing, right? So to answer this question, it's a local min for sure, right? But this other point over here is what we say neither. So this is neither. And the reason why is because it's decreasing here and it's decreasing here, right? It doesn't change from increasing to decreasing or decreasing to increasing. It's decreasing over the whole thing. It does have an inflection point, and we're going to talk about that in the next section. Any questions? Okay, moving right along. It says k is a continuous function with a critical point that satisfies k of 6 equals 10. And the derivative at 6 is what we call undefined. I think I put this up here, didn't I? Oh, here it is, critical points. So by definition, critical points will be where the derivative at a certain point is equal to 0. Right, that's why we found the derivative and set it equal to 0. Or it could also be where the derivative is undefined. And I'll show you an example of that. It doesn't come up too much in our class, but I'll show you an example where it's undefined. Or, of course, and we talked about that p-value, right, which makes the derivative 0, then that's going to be a critical point on the original function itself. Okay, so what we can say, what are the coordinates for the critical point? Well, we can say that since we know that the derivative is undefined at that point P, which is 6. And we know according to the rule above that I just showed you, if it's equal to 0 or undefined, then you can say that since K of 6 is undefined, then we know that it's a critical point, right? Now, that X value 6 is a critical point, right? So you can say that since K of 6 is equal to 10, we're interested in this 6 value, right? So K of 6 is a critical point. And they say that since K of 6 is equal to 10, the point we're looking for is the X and the Y value as a ordered pair. 6, 10 is the point. Now, if we want to figure out whether or not it's a local min or max, we have to do our interval tables using our critical point of 6. So we're going to say at 6, we have the numbers that are less than 6 and the numbers that are greater than 6. So if I use a test value, let's say K of K prime of some number X, they tell me in this actually I should put this so you understand where I'm getting this from. Okay, so they say here that for X is less than 6, you're going to get a negative number. They don't tell you what negative number is. They just, well, actually they do. They tell you you're going to get a negative 1. But for some number less than 6, and they're just not telling you what number it is. And then here, that if you take a number greater than 6, then they're telling you that the derivative is going to be equal to a positive number. So if this is negative and this is positive, then we know by the first derivative test that this is decreasing and this is increasing. So it's going from negative to positive. So to answer this question, is it a local min or local max? You're going to use the definition that says when it goes from negative to positive, right? Decreasing to increasing, you would have, what do you think? Local min or max? Think about a graph, a regular graph is a decreasing and then it starts increasing. Will it have a local min or local max?
Local min.
Yeah, definitely, right? Right, just think about decreasing, increasing. Now, what could the graph of K look like? And I noted before that, remember, this is K, the problem is undefined at 6, which means it has a vertical slope, right? So it could look like an absolute value problem. So it could look something like, let's say this is 6. Could look something like this. It could look like a lot of different things too, but basically like an absolute value, right? Because the slope going through that is never 0 because it's going down and then it immediately goes up. So it's just a vertical slope, which is also called undefined. All right, again, we don't use undefined critical points very often. It's just more of like a theory thing, like what would happen if the slope wasn't 0 ever, right? Okay, now here they want you to graph a function knowing all of this stuff. So let's look a little at a time and I will color. All right. So first we have critical points at x is 2 and x is 5. So I'm just going to draw a line here at 2 and a line here at 3, 4, 5. So we know that some points on the original function are going to be somewhere on either one of those or both of those things. Then it says that the derivative is positive to the left of 2, right? So what that means is that positive to the left of 2 and positive to the right of 5. This means that it's increasing. So let's see, it's increasing here, and let's say it's increasing here as well. And you could draw a number of different graphs above or below the x-axis. This could be. And then the other thing they tell you is that it's negative between 2 and 5. So a reasonable graph would be something like that. Now it says identify the critical points as local max, local min, or neither. Well, we have a local max here, right? And a local min here. And we don't have any inflection points. Or actually we do. It's right here. Because it goes from concave up to concave, or sorry, concave down to concave up. So this could be neither. And the reason why it's neither is because all along that blue line, it's decreasing the whole time, right? So that we would call neither. Any questions, anybody? No? Okay. All right, now, what you have to be careful of here is that this function, it says the value of an investment at time t is given by s of t. The rate of change, s prime of t, is what's graphed here, okay? So this is note, this is the graph of the derivative. All right, now the numbers above the x-axis are positive, and the parts of the graph that are below the x-axis are called negative. The critical points are always located on the x-axis of the derivative graph. Our critical points, we shouldn't say that, we should say our x-intercepts. So we can say, what are the critical points? That would be x is equal to 1, 1, 2, 3, 4, and 6. Now let's label this. We would say from this interval, it's positive, right? The above the x-axis, it's positive here and here, but it's negative in here, and then it goes back to positive. It's negative on either side, here and here. Okay, so let's take a look at this question. Identify each critical point as local max, local min, or neither. So let's say if, I shouldn't say x, I think I should be saying t. Let me erase that. And remember this, we're referring to time. Okay, so when time is 1, let's say, it's the value of an investment. So I don't know, let's say we're talking about years. So after 1 year, we will have neither a local max or a local min. And the reason why is because it's positive. So it goes from positive to positive. Positive to positive. So that would be this positive to this positive. And then if you look at t is equal to 4, there's 1, 4, and 6. I'll make the screen a little smaller. What we're going to on 4 is from a positive to a negative, right? Let's see. Positive to a negative. And if it goes positive to negative, we know that it's going to be a local max. Right, so think about something increasing, positive, and then decreasing. You would have a local max. And then if you look at t is equal to 6, then we're going from negative to positive here. So if you're going negative to positive, you have a local max. Or local min, sorry. Now they want to say like, okay, so what does this mean in terms of this investment? And remember, this is not a graph of the function, right? The value over time, it's the function of the derivative of the function, right? So if at t equals 1, it's neither a max or a min, it's going from positive to positive, you can say that it increases, basically the value of the investment is increasing until it stops increasing. Right? Okay, so that's what that tells us, is that it's positive and then it stops being positive. And then if you look at the t equals 4, remember t equals 4, it went from positive to negative. So what you can say is the investment peaked, basically, right? If it went from positive to negative, it peaked, then decline. And finally, at t equals 6 years, it starts increasing again, right, over here. See? So it goes down here, and then at 6, it starts increasing again. And increasing, I mean in value, right? We're talking money. Okay, here's the really interesting part. And I told you before that I'm going to have you like relay this back to what you learned about parabolas. I think some people are still writing. Everybody ready? Okay, so you guys should remember this function f of x equals, probably you remember it as ax squared plus bx plus c. That's the standard form of any parabola, right? Which goes with anything that's quadratic, meaning it has a 2 for an exponent, right? So we're going to do a little experiment here and say, find the critical point of that. Now, we know that the b value is usually a number, right? So if I was to find the derivative of that, I would use the power rule on the x squared, right? That would become 2x to the first power, plus, then I would use the constant b, and bx would just be the derivative of bx, knowing that b is a number, would just be the whatever b is, right? Well, then if I take that derivative and set it equal to 0, you would get 2x plus b equals 0. And then solve for x. So you have 2x equals negative b. Divide both sides by 2 to get x is equal to negative b over 2. Anybody recognize negative b over 2? What is that in a parabola? Anyone? All right, well, let's do this. Let's let the b value, I'm going to do a concrete example, equals 6. And let's say the c value is equal to 3. So what we have here is f of x is equal to x squared plus 6x, because I'm letting b equal 6, plus 3. So this is a real parabola, like pretend you're back in algebra 2. Well, what happens if we took the derivative of that and set it equal to 0 and solved it? So let's see, we would have, let's see, x squared would be 2x plus 6, right? And then so we have the derivative. And then actually, let me show that that's the derivative. So let's say f of x. Okay, and then like we've been doing to find the critical point, we put 2x plus 6 equal to 0 and solve, you would get x is equal to 3, right? But notice that if you said, all right, so for all quadratic functions, your critical point will be located at negative b over 2, right? So our b value in this example was 6. So if it was negative 6 over 2, it equals to, should this be 3 or negative 3? Oh, that should be 3. No, that should be negative 3. Minus 6, yeah, sorry. This should be negative 3. There we go. And notice that you get negative 3. So what they're saying here is for this standard form quadratic function, your critical point is going to be located at whatever negative b value is over 2. And what you should remember maybe from, and what are we saying? It's at negative 3. And 1, 2, 3, 4, 5, 6. So basically we have a parabola where the x value is negative b over 2, right? And this will work for any parabola. And if you figure out, okay, I know that's a critical point, so let's put that in the original function, then I could get this other value here, which ends up being negative 6. Or we could say f of negative b over 2. So you guys remember in algebra 2, when in order to find where the vertex is, you would just use that formula negative b over 2. Is it kind of ringing a bell with y'all? Yeah, good. But that's where it comes from. It all comes from calculus, right? Which is interesting. All right, so that's section 4.1. Let's see how much of 4.2 I can get through. Let's see. Not a ton in this section. Well, let me introduce you at least to inflection points, and then we'll do the rest of these notes once we're finished. Does anybody have any questions on 4.1? All right, cool. Let's go to 4.2. All right, this is all about inflection points, and you guys already know that from the other lesson that I told you when I pointed out if a graph changes from concave up to concave down, the point at which it switches is the inflection point. Also, I mentioned that I'm going to put up a extra credit assignment. I will be doing that. I'm waiting to get to the section where it makes sense, and it has to do with the COVID virus and the spread and inflection points. But we have to wait till we get to logistical graphs. That should be the next section. So here we go. Study of points on the graph of a function where the slope changes sign led us to critical points, right? In that last section, 4.1. Now we're going to study points on the graph where the concavity changes, right? Because notice that this is not, it's decreasing along the whole thing, right? But it does change concavity from concave up to concave down, or you could have it change concavity from concave down to concave up. Now, this is important in order to know where, the inflection point location is. If you're looking at a graph of f of x, which is what this is, right? It's easy to see where it is. It's just where it changes concavity. But if you're looking on the graph of the derivative, it's going to be wherever the local max or min are. And if you're looking at the graph of the second derivative, it will always be the x-intercepts. And we kind of figured that out on that one last example. All right, so that's concavity, and you just have to know where to look for the inflection point location on all three of these graphs. It's easy to tell where it is here, right, where it changes concavity. But then if you're looking at the graph of a derivative, it would be wherever the local max and min. And then we already did one example in the last section where we saw that on the graph of the second derivative, the inflection shows up at the x-intercepts. We just didn't call it an inflection point back then. Okay, so here's a graph, and this is my sketch of the graph, right? We're just going to verify that this graph makes sense. So we're going to first find the inflection points, and the reason and how we can do that is by setting the second derivative equal to 0, okay? So let me write that. All right, so the first derivative, let's find that first. We're going to use the power rule, so you get 3x squared minus 18x. Write this so you guys can read it later. Minus 48. Then to find the second derivative, we need to do it again. So you'll get power rule here, what we have 6x minus 18. So now we're going to set that equal to 0 and solve for x, and we should get x is equal to 3. So here on this little sketch we made, notice that the x value of the inflection point is at x is equal to 3. So this value here would be 3 with some y value. And now let's just confirm concavity by doing an interval and see what happens concavity-wise when x is less than 3 and when x is greater than 3. So here's 3. So let's do a test value. Let's see, the second derivative at a number less than 3, let's say 2. You put that in, you're going to get a -6, right? So we know that the second derivative is less than 0. And it would make sense because it's concave down on all the x values less than 3. Yeah, less than 3. So concave down. And then if we put a number greater than 3, let's say 4, you're going to end up getting a positive number. So the second derivative is positive for numbers greater than 3. And because it's positive, that means it's going to be concave up, which it is. So we've just confirmed that this graph is going from concave up to, concave down to concave up. And because it changes concavity, we have confirmed that x is equal to 3 is the inflection point, at least the x value of the inflection point. All right, I think we're done for today. I think your next Wiley assignment is up. May not be though. All right. I'm writing that down now, post Wiley. I'll do it right now. I have 3 people that needed to see me. So the rest of you are free to go.
Thank you.
Thank you.
Thank you guys.
Thank you.
It's Kelly, because we need to set up an appointment for tomorrow. All right, let's start with James, since you were first to ask.
Can we do tomorrow at 4:30?
I think Thursday, yes.
That's cool. Okay. Thank you.
And that is James.
Yes.
All right, I'll see you right here.
All right. Thank you.
You're welcome, hon. All right, Dylan.
Can we do tomorrow at 12?
Tomorrow at 12 might be tight for me. Can you do 1?
Yes.
Or even 12:30 if that's better for you?
Yeah, I have a class at 1:40, so however long it's gonna take. I mean, either's fine.
Oh, okay, so 1 o'clock would be better for me.
Okay, that's fine.
All right, Dylan, see you then.
Thank you.
Mm-hmm. All right, and Matt.
I'm available anytime after noon tomorrow, so whatever works.
Afternoon, so let's say, how about 12:45?
That works.
Okay, I'll see you then, sweetie.
Thank you. Have a good day.
You're welcome. You too. Tom, what can I do for you?
Hi, Professor. As you probably know, I bombed that last exam. I was just wondering when the next exam is and if there's any possibility of like doing extra credit work or
Yeah.
perhaps even retaking the exam.
If you're listening earlier, I am going to post an extra credit assignment that should, if anybody bombed one of the tests, that should pull them up and as long as they do well on all the other tests and the exams.
Okay. When can I expect that?
So that's coming, I would expect by next class, because I don't want to post it before you guys know the information, okay? So by
Got it.
next class, and so there's extra credit. And what was your other question?
Just when the next exam is.
Oh, that's listed on Schoology. It's on the, what do you call it? Pacing guide.
The what?
The pacing guide.
Oh, okay. All right. That's all.
I could look it up for you, but you might as well know
I
it.
can just do it myself.
Yeah,
All
okay.
right.
All right.
Thank you.
We're going to be online from this point forward.
Okay.
All right.
All right. Thank you.
You're welcome. Have a great day, sweetie.
You too.
Thank you.
Bye.
Bye.